Thank you. Me again, I'm sorry. Just when you thought it was safe to go back to the lecture, it is me. The good news, there's good news. After this lecture, there are only 2 more that I have. So, okay. So now we're talking about a little bit of dynamics, about mid-latitudes and why the flow goes round in the direction of the Earth's rotation mainly and does not go so much in the meridional direction. And why we get jets, and in particular, for example, why on planets like Jupiter we get even more jets. So, for example, speaking of Jupiter, oh, it works. There's Jupiter, and you see the famous bands. Okay, so let's try this. The famous bands on Jupiter. Also, you can see them on Saturn, like this. There's Uranus and Neptune on the right, and not so apparent. But on Earth, let me see how it works. Here's just a snapshot of the daily weather on Earth here, but here is the averaged, the time averaged flow in each hemisphere as a function of latitude and height, and you can see both strong jets in both hemispheres. And in fact, in the southern hemisphere, it appears that there are 2 jets. The jet here on the left is much more vertically uniform than this jet here. This jet here is actually the jet which is at the edge of the Hadley cell. And it has quite a lot of vertical structure in the vertical. And that's just a consequence of the thermal wind, which we talked a little bit about. There's a strong temperature gradient. If there's a strong temperature gradient, east-west, north-south, then there will be a shear in the atmosphere, and that is what you see here. But here, this jet is a little bit more vertically uniform, and that is not particularly a consequence of the thermal wind. It is a consequence of the turbulence in the atmosphere, which organizes itself to give you a jet. It's large-scale turbulence in the atmosphere, sometimes called geostrophic turbulence or macro turbulence or large-scale turbulence. It occurs on time scales of weeks and on the space scales of hundreds of kilometers. So it's a large scale. It is weather, if you will. It is the weather, but it organizes itself to give jets. And here's another picture. And here it is again. This is a different set of data, but this jet here at higher latitudes, at about 50 degrees north, is actually also associated with a maximum in the surface wind. And anticipating a little bit, what that jet is due to is that the eddies, the weather in the atmosphere, they organize themselves and they converge momentum into the jet. They have an upscale transfer of momentum. It's sort of an anti-diffusion, if you will. So normally when we think of diffusion, we think of it as getting rid of maximum. These jets organize themselves and transfer momentum against the gradient and cause there to be a jet. Oh, okay. Oh, the word. Oh, I haven't labelled it. Okay. Let's see if I can find it. Oh, this is about 8 kilometers high. 8 kilometers, something like that. Yeah. I haven't labelled it for some reason, but about 8 kilometers. something like that. It's in the upper troposphere. And it's about 30 meters per second. When I say it, surface wind is 10 meters typically. It is 0 at the actual surface because there's a no slip condition. But the surface wind is about, typically, by convention, it is at 10 meters high. And here it is again, just a different. This one was a NOAA reanalysis, just to show you that it's not dependent upon who is fiddling with the data. This is Japanese interpretation of what the data is. And it coincides more or less with the surface wind because there's a convergence of momentum, which we'll talk about soon. And that convergence of momentum, you have to get rid of that momentum somehow, or it would keep on accelerating forever. And that convergence of momentum is balanced by a drag at the surface, which takes out the momentum, and hence the wind is the maximum. It's stronger in the southern hemisphere. The dynamics is cleaner, if you will, in the southern hemisphere because there aren't as many continents. And continents just add another layer of complication to the subjects because of stationary waves and mountain waves, and less so in the southern hemisphere. Okay. Just one other little thing. You see here that the winds are also westward near the equator. Meteorologists have this funny convention that a westerly wind comes from the west and an easterly wind comes from the east. And I think that's just historical, really, because where the wind comes from tells you what the weather will be. If it's coming from a cold place, then it becomes cold where you are, so it tells you what the weather will be. Oceanographers have a different convention, and they talk about, because they want to be different or something. And oceanographers talk about westward currents, which are going to the west, which is in a way more sensible. But here the winds, and what is actually true is if you integrate over the entire surface, the winds exactly cancel out on an integral basis. There are as many eastward winds as westward winds. It's not quite obvious, perhaps, from this. It looks like there are more westerly winds, but don't forget, there's a cosine factor when you do the integration over a hemisphere, because there's more area at lower latitudes. And of course, it has to pretty much cancel out. Otherwise, there will be a net transfer of momentum from the Earth to the atmosphere, and the atmosphere would spin up. So it has to integrate out to zero if you're in a statistically steady state. And in fact, just as an aside, there are fluctuations, day-to-day fluctuations, and it doesn't exactly cancel out instantaneously. And we can now measure the rotation rate of the Earth, and the rotation rate of the Earth, the day length of the Earth, will change ever so slightly from day to day by something like maybe 1/100th of or 1,000th of a second from day to day. And that's because of the transfer of momentum from the Earth to the planet. But for you and I, it's 24 hours. Okay. Yeah.
Yeah, I have a question on the slide before. On the card, where is north and where is south?
Okay.
You said in the northern hemisphere.
Yeah. Okay. Here, let us look. This is south. And the convention is that southern hemisphere latitudes are often negative. So this is south. This is south. So these winds are very strong in the southern hemisphere, not so strong in the northern hemisphere. And these winds at the surface, where are they? Sailors call these winds the roaring 40s. And they are typically just off the tip of South America, and there's no continents in the way. So they are very strong. So there's the roaring 40s here, and then the furious 50s, they are called here. And we talked about the Hadley cell yesterday. We said that in an ideal Hadley cell, which will be an axisymmetric planet, when there's no variation in longitude and no eddies at all, that we would expect the wind to be angular momentum conserving. So if we do a simulation, the top simulation is of a planet which has no variation, no eddies in longitude. This dashed line here is the angular momentum conserving wind, i.e. each position on that has got the same amount of angular momentum. The angular momentum basically is proportional or varies like the wind times the distance to the axis of the center of the Earth. So it increases very rapidly with latitude. And an actual simulation, numerical simulation, shows that the wind does almost follow this angular momentum conserving wind. It increases very rapidly. Once we do a more realistic three-dimensional simulation, you get this pattern, in which case the wind is no longer angular momentum conserving. It's much smaller, and that's because the eddies, as we will see, have transported momentum away from the tropics into mid-latitudes. And at the same time, the Hadley cell and the Ferrel cell are much stronger than they are in an axisymmetric circulation. So, obviously then, just from the observations or numerical simulations, we know that the large-scale eddies are going to be important. And the way that they work will be the subject of the next few slides. Rupert. Good thing you weren't in the lecture yesterday. Go on. So here.
Yes, at 15 degrees.
Oh, here.
And you have a change on the slope.
In the surface wind or the oh, just here.
Yeah, yes. So is it known what's happening? What makes that special?
Oh, I don't know. It will be some kind of an eddy effect, where they begin to dominate. Yeah, but why it exactly does that, I don't know. But the eddies will start to dominate at higher latitudes. between 0 and 20 degrees latitude, the eddies are not so important, and the tropics are fairly axisymmetric. And you don't get storms apart from the occasional hurricane. In mid-latitudes, they are dominant, and we'll see in a second. Now, so let me just explain what the balances are in the ferrule cell. And my notation will be that for any field, for example, U is U bar plus U primed, and that is an average result, typically a zonal average. So it's the integral of U dx over the length around there, and this is the eddy. Okay, and in the ferrule cell, this is towards the equator, this is at high latitudes. Ferrule cell circulates like this, and the balance is between the Coriolis force and the eddy terms at high altitudes. F is the Coriolis parameter, V is a meridional wind in the north-south direction. That's balanced by the eddy convergence of momentum. And that is of a particular way that gives you a wind which is blowing from north to south. And that's balanced in the vertical by R, which is R is the drag, it's the friction times the surface wind. So if you integrate vertically, there's a momentum balance. And similarly, the vertical velocity is balanced by an eddy term, but now it's by an eddy term involving the temperature theta. Okay, and if you look at the momentum equation, I've left out a few terms here, but the dominant balance, there's the acceleration, the Coriolis term, and d by dy of u prime v prime is an advection term, but it's an advection that involves the eddies. And the same in the temperature equation. N squared is just the vertical derivative of the average temperature. And it's these eddy terms which are important. And why do they work in that particular way? And the other thing that the eddy terms do in a steady state, when there's no acceleration, there's a balance between the Coriolis and the eddy terms. But at the same time, these eddies are producing an acceleration which eventually halts. But you can see that if you go back to this equation here, and if you're in the upper atmosphere, this friction is small, that this eddy term, this eddy convergence term, would also produce an acceleration, a positive acceleration, and that acceleration is accelerating the wind to the east. It's producing a westward wind. So the eddies are, in the steady state, they're producing this ferrule cell. At the same time, they're going to accelerate the wind. And we'll talk about why do they do that? Why do they have this particular pattern? Why aren't they producing another pattern like that? Another pattern which might have some other effects. Why do they accelerate the wind in a eastward direction? And the answer to that lies in the effects of Rossby waves. And this was actually first elucidated by an oceanographer called Rory Thompson. He was an odd character. His first name was Rory, which is not so odd. But he submitted to journals, and he liked his first name. But the journals would always just put his initials on the journal. So he changed his middle name, and he added 3 middle names, beginning with O, R, and Y. So in the journal, it would actually be R.O. R.Y. Anyway, enough. So why are jets a ubiquitous feature of planetary atmospheres? What determines, and on Jupiter, as we saw, there are multiple jets. Why are there multiple jets? So let's start with the simplest possible model of this, which simpleness perhaps is in the eye of the beholder, but I'm going to talk about the vorticity equation. Here it is in 2 dimensions. Zeta is vorticity, u is the vector velocity. And how do we get this equation? Because in 2 dimensions, absolute vorticity is a Lagrangian conserved quantity. It has this d zeta a by dt is F minus d, forcing minus dissipation, whatever they may be. Zeta a is the relative vorticity plus the vorticity due to the planet's rotation, which is just F, the Coriolis parameter, twice 2 omega times the sine of latitude, because it varies with latitude, and the vorticity itself in 2 dimensions is just dv dx minus du dy. V is the north-south velocity, u is the east-west velocity. So there's no vortex. If you're a 3-dimensional fluid dynamicist, you think there's vortex stretching. If you just think of 2 dimensions, there's no vortex stretching because there's no 3rd dimension. So vorticity is conserved, apart from the effects of viscosity, which we'll come to. So d zeta a is conserved. This is the material derivative. We expand that. We get the material derivative of relative vorticity plus this term, beta v. Beta is just df dy. This is, if you will, this term here is v df dy. Just if you like, it's the advection of planetary vorticity. So this, which will be very familiar to those of you who have a meteorological background, is just a conservation equation for vorticity. It's the equation of motion in 2 dimensions. It's a key equation. If you have any questions, now is the time to ask about that equation. Okay, so the fundamental reason why the flow organizes itself into a zonal direction is this term beta. And suppose we have a simulation and we've got some steady state, we have some forcing and dissipation, and we integrate this equation numerically. And then we decide in our numerical simulation we're going to turn up the value of beta. We're just going to, we have a little dial on our computer, we turn it up. We keep everything else the same. So we can write that term, if you like, as beta v is just everything else. And it has to balance. This is an equation. It has to balance. We're forcing it to balance. And then if we turn up beta, that term itself can't dominate. We can make beta as large as we wish. That term cannot dominate because it's an equation. So v has to become smaller. Otherwise, there's nothing to balance that term. So v becomes smaller. So if we spin faster and faster, beta increases. V must diminish if all of the other terms remain the same. So if beta is big, v must be small, which is the meridional velocity. So that must diminish. But if the forcing and dissipation remain about the same, the zonal velocity will stay about the same. So we'll get a zonal flow will dominate. Now that's not an argument that will satisfy a true mathematician. They'll say, oh, this is hand waving. You haven't shown this at all. How do we know that it doesn't do something else? But it's a kind of argument that meteorologists will use, and it's a reasonable argument. And it turns out to be a true argument from numerical simulations. But it doesn't explain why we get jets, why we get alternating jets on a planet like Jupiter. So, how does that happen? That happens because the flow looks something a little bit like this. In midlatitudes, the zonal flow is actually unstable due to bioclinic instability. There's a hydrodynamic instability, and that gives rise to weather. And that instability is actually independent of the fact that the Coriolis parameter is changing, of the fact that beta could be 0 or non-zero. But we get mid-latitude weather. So imagine that this mid-latitude weather, imagine that we go back to our two-dimensional fluid, and imagine instead of there being we'll mimic the effects of a true hydrodynamic instability by taking a two-dimensional fluid, could be in the lab, we'll put a spoon in it and we'll stir it. And that stirring is kind of the effects of the instability. We'll design the stirring so that it doesn't put any momentum in itself. It's a stochastic forcing, if you will. Okay, so this we're going to stir, and we're going to stir just in mid-latitudes. And what happens is that's going to create Rossby waves. And Rossby waves, which we'll come to in a sec, are the kind of waves, the large-scale waves which occur in the atmosphere, wavelengths of 1,000 kilometers or more. They actually must propagate away from the disturbance, because even though we're not putting momentum in, by stirring we're putting energy in, the Rossby waves carry that energy away. And it turns out, next slide, we'll show it, that momentum travels in the opposite direction of the Rossby wave group velocity. And these Rossby waves then converge in the region of stirring and give you an acceleration. And how it works in physical space is this one on the right, that they create these boomerang-shaped eddies. The flow goes round like this. And here, for example, U is negative, V is positive, so UV, the product, is negative. UV is also negative over here, but UV is positive on the south side of the stirring area, which is here. So d by dy of U times V is negative, and that will converge momentum in because the acceleration of the flow is proportional to the negative of d by dy of U times V. Now, why should that be? And here's the mathematics behind it. And as I said, this argument actually goes back to this oceanographer called Rory Thompson. Here's our equation of motion. I've used Q here instead of zeta I, but it's just the absolute vorticity. In 2 dimensions, zeta plus F. Now, if it's two-dimensional and incompressible, the divergence is 0. We can replace the flow, or we can use a stream function to derive, to describe the velocities. U is d psi dy, V is, oops, there's a typo here. V is d psi dx. So we introduce a stream function to describe the flow. Okay, and then we'll linearize this equation. And in here, the simplest way to linearize is actually just to toss out, this is the advection term. We'll just throw that away, so we have d zeta dt is beta d psi dx. D psi dx is V. So this is just the same equation we had from a couple of slides ago. And then, once we've linearized, we look for solutions which have this form. E to the I kx plus ly minus omega t. We do the standard, we linearize in a standard way, we find the dispersion relationship. And you've all done this, maybe you haven't done it for Rossby waves, but it's just a very standard thing. And then you get the dispersion relationship. Omega is minus beta k over k squared plus L squared. K is the wave number in the zonal direction. L is this wave number in the meridional direction. E to the I kx plus Ly minus omega t. And then, once we've got the dispersion relationship, we can get the group velocity. We can get the group velocity in the meridional direction by differentiating the frequency with respect to L, the meridional wave number. So this is the group velocity in the meridional direction, and we get this expression, just d by dl of this expression, which is 2 beta kl over k squared plus L squared all squared. And everything here, beta is positive, k squared plus L squared all squared is positive. So the sign of this is proportional to k times L, the wave number in the x direction times the wave number in the y direction. And now let's go back to looking at what the u and v are. U is d psi dy, v is d psi dx, fixing this typo. D psi dy is IL times this expression. D psi dx is ik times this expression. uv is minus c squared kl. Just do the algebra yourself after the lecture if you want. So, if we have a Rossby wave, it's creating waves, and that Rossby wave is fluxing, creating a momentum flux, and that momentum flux is proportional c minus c squared k times L. So the momentum flux is minus k times L. The group velocity in the y direction is plus k times L. So the group velocity, now we're making, is that a question you had or just? Oh, just a wave, hi.
There's some C's missing because the group velocity on the left-hand side is a velocity, and on the rightmost it's being held similar to a velocity squared. Right? The units of del omega del L are velocity, whereas the units of over bar uv.
Yeah, it's true. Well, I mean,
I think it's a c squared.
yeah, it could be, but this is not an equal sign.
Yeah.
It's a little squiggle, which means it's okay that I missed out a c squared. So the units are okay if you allow me a squiggle instead of an equal sign. And since this is a lecture, not a textbook, we're allowed to make squiggles. So we're all good, but well spotted nonetheless. But it's a sign which is the key thing. The uv is minus kl, and the group velocity is plus kl, because everything else is positive. And then the key thing, which is sort of a kind of a causality argument, is that the group velocity has to be directed away from the disturbance, because the group velocity carries energy with it. When you look at waves, there's the phase speed, which is the speed that just the phases of the wave is moving at, but it's the group velocity which is carrying the energy and other properties. And since we're stirring here, we can argue that the group velocity must be directed away from the region of the disturbance. And that's a physical argument again. So, if the group velocity is directed away, so up here, the group velocity is positive, and KL must be positive. Down here, the group velocity is going away from disturbance southwards or towards the equator, and so KL is negative. And that tells you how the momentum flux is. And the momentum flux is in the opposite direction to the group velocity. So the momentum flux is towards the region of the stirring. And so if the momentum flux on both sides is towards the region of stirring, it means that the Rossby waves will be converging momentum in the region of the stirring. Okay, so if I just summarize the whole thing on the board, Roswave source here, CG in the y direction, CG in the y direction. This is mid-latitudes, about 45 degrees. And because the momentum flux is the other direction, UV is negative. Momentum flux the other direction, UV positive. So d by dy is negative. D by dy is negative. In this region here, du by dt, which is minus d by dy of uv, is going to be positive. So it's going to accelerate the flow here. And then if we put a Coriolis term in there too, it's also going to produce a meridional velocity. And exactly which one it will affect more, you'd have to do more work and solve the equations. But it will both accelerate the flow, which will give you a jet, and it will also produce a meridional flow, which is the Hadley cell. And typically, V is small, also, another way of thinking about it, just in the momentum equation, there's various terms. Meridional flow is multiplied by F in the momentum equation. F is large. It's the Coriolis term. It often is a dominant term. F is large. V tends to be small simply for that reason, that it's being multiplied by a large term. But going back to this picture, it's because you're creating Rossby waves here, which go away from the source region and converge momentum back into the source region, that you get a jet. Yes?
I wanted to ask two things. First of all, physically, how can it be that energy is transported in the opposite direction of momentum if momentum also?
Momentum isn't transported quite in the same way. There's no, yeah, it's a good question. And I think it's, I don't have a immediate answer except that to say that momentum, there's no reason why momentum and energy are transported in the same way. Momentum is a funny thing because momentum isn't conserved in the got all these various terms. We've also got a dp by dx term. So pressure also affects the momentum, and it's not transported in the same way by the group velocity. And I don't think I have a quick explanation for that. Good question. I'll think about that. Was that your? Did you have a follow-up question? Was that?
Yeah, and I wanted to ask why is this stirring happening at the midlatitude?
Why is it happening? Okay, I haven't explained that, but it's because only in mid-latitudes do you get a condition for instability. And there's a few reasons for that. I wonder if I have the... Let's look at the flow, the basic state flow, either this one or this one, if you will. That the shear, the instability arises because of a shear in the vertical between the upper level flow and the lower level flow. And you only reach a sufficient shear in mid-latitudes if you actually look at what the low latitudes, both here, which is sort of the basic state, there isn't enough shear. So it's only when you get up to here or so that there is sufficient shear to give you an instability. And basically, that arises mainly in mid-latitudes. There's a second reason to do with the variation of the Coriolis effect that also inhibits instability at low latitudes. But both act in the same way, that it's only in mid-latitudes do you get this condition for instability. And there's a question, but yeah.
Just a quick one. So, like you explained yesterday, the wind is the fastest at the equator if you just take due to the rotation of the Earth, and as it moves forward, it carries with it in the this force, the momentum. I'm wondering how the momentum convergence from the pole happens physically, because I'd imagine that just driven by the pure rotation, it would be the slowest. So how is the momentum coming from?
No, it's in part the wind is actually slow here. Because you've transported wind, because you've transported momentum from the pole regions into mid-latitude regions. I mean, in a sense, that's partly why the wind is a maximum here, rather than at lower latitudes. I mean, the actual relative wind, if we were purely angular momentum conserving wind, the wind would be enormous at the poles. I mean, this would go on and be hundreds of meters per second. So in the absence of this instability, there would be a very large zonal flow at the poles. But it's not angular momentum conserving, but it would be in the basic state if there weren't any of these winds. Okay, so how am I doing? A few more minutes. Here's just the same thing again, but the bottom line is here. That it's the opposite of the group velocity. Of course, Jupiter, I'll go through this a little bit more quickly. Jupiter has multiple jets. it doesn't just have one jet, it has multiple jets. Why is that? It's really because on Jupiter, the source of the energy is not just baroclinic stability. That in fact it's a research topic as to what the source of the energy is. It's not fully understood. But the general feeling, or at least my feeling, which of course should be the general feeling, is that it's coming from convection underneath. Jupiter is being heated very rapidly beneath. So, and convection is bubbling up into the weather layer where we see what's going on. And so the energy sources are very small scales. And because it's a very small scales, what happens in two-dimensional turbulence is that the energy, this is a simulation on the right-hand side of two-dimensional turbulence. This is the energy spectra, it's a function of wave number. You're forcing at very small scales, and then the energy cascades to large scales through an energy cascade, which if you study turbulence at all, being fluid dynamicists, you'll know that there's an energy cascade from where we are forcing it, the scale at which we are forcing it, to some other scale. In three-dimensional turbulence, because there's a vortex stretching term, it's cascaded to small scales. Two-dimensional turbulence, which is more or less the kind of turbulence which occurs on planets, because the aspect ratio is very different. The energy is cascaded from large scales the energy is cascaded from small scales to large scales, like here. And then once you get up here, you're at large scales, then Rossby waves kick in again. Okay, and the Rossby waves kick in again, but now there's no particular region defined to be the forcing scale in physical space, like there is in midlatitudes. There's no preferred region of instability. There are potentially many regions of instability. And so the upshot of that, without going into details, is that you will get multiple jets on Jupiter. Because there's no preferred region, and you'll get let me see if I can find a particular that if you actually, for example, do a two-dimensional simulation of Jupiter, when you have the forcing at very small scales and allow it just to cascade through the turbulent flow to larger scales, then you get multiple jets depending upon the parameters in your regime. And if you actually look at the scaling, again, physicists like to look at scaling. Pure mathematicians think it's black magic because you're sort of assuming the answer. And I should say, you know, I'm much more of a physicist than a mathematician, but we actually need mathematicians as well. And it really is a, you know, sort of, or should be a synergistic relationship between the two to bring a little bit of rigor to our subject, to stop us physicists going off into some la-la land. But if we scale the equations, take these equations, look at the advection term, it scales like U over L, where U is some velocity, L is some length scale. The beta term scales like beta times u. So there's a crossover scale. If you say that you'll get jets where this beta term is approximately the same size as the advection term, then you get a scale here, which is the scale of the jets. And if on your planet, that scale is much smaller than the planetary scale itself, then you will get multiple jets. And that happens to be the case on Jupiter, and it may well be the case actually in some regions of the Earth's ocean, that this scale here, square root of u over beta. On Jupiter, it's about a few thousand kilometers, but the radius of the planet is 60,000 kilometers. If you put in the numbers for Earth, this scale u over beta ends up still being a few thousand kilometers, but the planet's scale is only a few thousand kilometers, so you can only get one jet on Earth. So that's why Jupiter is different from Earth, apart from the fact that it's made of hydrogen. But, anyway, I will stop there. I think I've run out of time and everything else, so I'll stop there. Thanks.
Hello, thank you again for part 3. This might be a silly question, but obviously the rotation rate of Earth is determined by the rotation rate of the surface, such that a wind which is at rest with respect to the surface, there's no drag or whatever. How do you determine the rotation rate? What is an appropriate rotation rate for a gas giant?
Yeah, well, that is a question which people debate endlessly. The standard thing is to look at the rotation rate of the inner planet, which you can measure because you look at the magnetic field.
Oh, yeah.
So you use that as a reference state, and so that is what we use. Now, just to make another little point about Jupiter, let's go back way to the beginning. I can find a picture of one of. No. I thought I had I do somewhere have a plot of Jupiter. This one. So we take the magnetic field as a reference. But you could imagine taking something else. There is no solid. The question essentially addresses the matter that on a gas giant there is no surface to speak of. It's gas all the way down to the center. There probably isn't even a solid core on Jupiter. But suppose we actually took something else just for laughs, and we took something else. We will still have multiple jets on Jupiter, so that doesn't affect that picture, but it does make a. But that's what we do, and in a sense, one's hope might be that once you get down far enough, that the planet is rotating more or less as a solid body associated with the magnetic field.
Okay, thank you.
Don't forget, in terms of asking questions, if you have a question, whatever it is, there's probably 10 other people who have that same question. And they're kind of, sometimes people are too shy to ask, but you're not just asking for yourself, you're asking for other people. So it's a generous thing to ask a question.
So In that spirit, yesterday when you showed us the Hadley cell, there was a jet at the top of the Hadley cell when everything was falling down. And today, the jet, I'm imagining, is a different kind that we are talking about in the ferrule cell.
Yeah, that's right. Yeah, exactly. Let me go back to. Let me go back to this picture. The jet. This is just yesterday's plot, if you will, and the jet peaks at about 30 degrees, and it's got a lot of shear associated with it. The surface wind is almost zero, and it's just due to this angular momentum conservation. When we add the eddies and so on, this jet actually shifts polewards. See, it's now at about a much more poleward latitude. So that is, in a sense, a different jet. Now down here, there's still something of a, here, and here, I guess also you can see the surface wind is higher because of the angular momentum convergence at the top is balanced by the drag at the bottom. So so this is a different form of jet. Now both jets, maybe this is an answer to Rupert's question earlier. You still do get the remnants of this jet here, and that still exists. And if we go back to the observations, it's especially clear here in this picture. You can kind of see both of them, and if you actually look, more localized and in different seasons and so on, you'll actually see them. They can actually be quite well separated and distinct. When you look at the observations, once you've averaged sufficiently, they tend to merge and all become one. But Rupert asked this question as to why this was a little bump here. And perhaps the answer to that is that this is a little remnant of what the subtropical jet is, but instead of coming down there, I think that is actually this jet here, maybe similar latitude to where the subtropical jet is. So. There's another question here, I think.
Yeah, I wanted to ask, could you maybe explain where the 2D turbulence matters on Jupiter in order to create these jets?
Yeah. Well, of course, that's another research question, really. And here's Jupiter. And it's sort of got various layers like this. And this interior I suppose, is fairly quiescent, but it's hot. Energy is escaping here. And then this region is convective. So you're just getting convection, like Rayleigh-Bénard convection. And so you get lots of plumes carrying heat. And two-dimensional turbulence occurs in two ways. First of all, Jupiter is rotating like crazy. It's going around every 10 hours. And it's 10 times, Jupiter's 10 times as big as Earth. So in a sense, the key thing when you're looking at the effects of rotation, well, actually the rotation rate times the radius of the planet. So it really is rotating quickly. What that does is it constrains the convection here to actually lie along the axis of rotation and not to be like this. And then this layer is called is sometimes called the weather layer. And that's a layer that you can see. And the two reasons why you might get two-dimensional turbulence. First of all, this weather layer is a little bit like Earth's weather layer. It's stably stratified. And this weather layer, it might be 100 kilometers thick, but this distance is 100,000 kilometers. So the aspect ratio is such that it is two dimensions. And this convection these plumes are quite small and they're forcing the weather layer. And so in the weather layer, it's kind of two-dimensional. So you get, arguably, and again, it's not really known that the flow in here is two-dimensional, or quasi-two-dimensional, in the same way that it might be on Earth. The other argument well, the layer below the weather layer is more or less unstratified because it's highly convective. It's highly convective, and so that just gets rid of all it's not stratified at all. It's basically adiabatic. Exactly, yes. Yes, that's right. So you get, this is unstratified. The heat is transported out by convective plumes here. But here, the weather layer is stratified, and again, Rupert has put his finger on why this is stratified. It's because you have to carry away heat, but now radiation takes over from the convection, and this is a stratified layer. And it's also the case, Jupiter's kind of interesting. It gives you free rein to the imagination because there aren't so many damn observations to tell you that you're wrong. It's because this is so highly rotating, you get something called the Taylor-Proudman effect, when there's very little variation in the vertical. And you get Taylor columns in the convection, and that gives you a sort of a quasi-two-dimensional nature. There isn't any variation in this direction, so it becomes two-dimensional in a certain sense. So, but all these are, in a sense, research questions and I don't have a definitive or crisp answer for you.
So I think that we have to stop now because I'm a bit late and if we want to have lunch. So let's thanks again